Hi everyone, my name is Christian Miles, and I've been working with graphs and graph databases for about 15 years. My talk is about a Postgres extension called Apache AGE that helps you run graph workloads on top of relational data stores. I'll be walking through the graph database landscape and where AGE fits in and how it compares with other extensions like PG routing. And then I'll focus on something I'm really passionate about, graph data visualization, when to reach for it, when to reach for Apache AGE, and the pitfalls to avoid along the way. Let's dive into querying and visualizing graphs in Postgres with Apache AGE. I'm Christian, and I'm based out of Victoria, BC, far left of the map there, the very bottom of that little island. My accent gives me away. Originally, I'm from the UK, but I've been in Canada since 2012, and I've been working with graphs, graph databases, and visualization tools for close to 15 years now. I wear a lot of hats, some sales, some engineering, some product, but the through line for me is helping people do useful work with connected data. And I'm here today with gdotv. We make a dedicated IDE for querying, visualizing, and debugging graph data. So here's the plan. I'll do a quick pass through the key questions I get asked about graphs, what they are, why there are so many databases, and where Apache AGE fits. And then I'll spend the rest of the time on visualization, what works and what doesn't. Here's a slide with a bunch of pretty things. We have a flow chart in the top left overlaid onto a map. We have a Sankey diagram in the top, a version control graph from Git on the right, a circular dendrogram, as it's called, right there in the middle with the bundle edges, and a network model of a mouse brain on the far left at the bottom there as well. And there's a few others on the slide. But these pictures all have something in common. They're all graphs. Yes, all of them. And there's no shortage of names. Networks, charts, maps, topologies, they all share a common property. They're built from connections between things, nodes and the relationships between them. And that's a deceptively simple set of building blocks for representing quite complex ideas. Okay, I'm already kind of off the rails with the FAQ, but is this a graph database? No one actually asks me this, but it's a really common misunderstanding. And one thing I'm a bit of a stickler about is that many graphs are not actually graph databases. A graph can be as simple as a CSV where there's a source column and a target column. It can be two relational tables with a foreign key between them. A graph is just simply a way of thinking about data that prioritizes connections. A graph database is a system built to store and query that structure at scale. A classic example of a graph is a social network, the graph that underpins Facebook or, say, LinkedIn. In the commercial world, you see a lot of graphs in know your customer and compliance work, following chains of payments across accounts, institutions, jurisdictions, anywhere the relationships between entities are just as important as the entities themselves. And briefly, the sorts of questions you're asking of a graph data depends to be different from relational queries. Things like how many hops between two entities? What's the shortest path? Which nodes are most central to a network? There's a whole field of graph analytics that operates on this connected structure. I'm not going to go deeply today, but it's worth knowing that there's an analytical layer sitting on top of what I'm about to show you. But it struck me recently that there's no resource to understand the full landscape of graph databases. So I put together a site called gdbengines.com. It lists all the graph databases I could find, along with some important categorizations. Most people hear about graph databases through Neo4j, and they've done fantastic work popularizing the technology. And for some people, Neo4j is synonymous with graph databases. But as you can see from this partial list here, there are over 100 different graph databases, and they differ in important ways. Three categories matter for today. There are native graph databases, where the graph is sort of a first class concept baked into the architecture, extensions, where a relational database has been extended to do graphy things, and query engines, which sit as an analytical layer on top of the existing data store. Now, the next question I get asked after seeing all these databases is, which is the best one? And I'm going to give you a classic engineering answer. It depends. It depends on your current stack, your data volumes, whether you need graph and relational data together. One underestimated consideration is, what does your team already know? Familiarity with a query language or particular technology or stack is important. And then the final thing I'll mention in terms of the considerations here is that, is this your primary data model, or is it an analytical overlay on top of existing stores? These are all different requirements. Because graph databases prioritize connected data, they come with query languages designed for that structure. I've got a few on the slide here. I put together this little timeline. Our product is called g.v as a reference to the Gremlin query language, one of the first we supported. So you can see there in the top right there under Gremlin, you can see the g.v with the open bracket, close brackets. That's a sample query there because it represents graph.vertices, yet another name for nodes. Gremlin models traversal as a first-class operation, which tends to appeal to people who think about graphs mathematically rather than declaratively. A traversal is simply walking from one node to another along edges in a graph, the fundamental operation in any graph query. I want to spend a little time talking about Cypher here in the middle of the slide. It lets you query using what's essentially ASCII art, so a little like text representation of the graph that you're querying against. You write patterns that look like the connections you're describing. A lot of people find this really intuitive, and it led to the open Cypher standard, which is now used across multiple databases. Now, I've included GraphQL on this slide too, because it's a common source of confusion. GraphQL is an alternative to REST for API queries. It lets you do nested selective queries against endpoints, but in itself, it's not actually a graph database query language. Now, some database vendors have muddied this by using GraphQL as an interface, but those are different things. And then GQL there at the bottom of the slide. You can think of this as a formalized standards body-backed future for graph query languages. More collaboration, more convergence. And to answer the original question, SQL PGQ is a parallel effort bringing graph pattern matching into SQL itself, part of the SQL standards since 2023. And you can see there that at the just above GQL at the bottom of the slide. I'm going to take a little bit of a diversion again and talk about knowledge graphs. This is one term you may have heard of. It gets applied nowadays to basically any system that aggregates information across an organization. So the marketing usage of it is broad. But a more rigorous definition of this pairs data with an ontology, which is a formal model of the types, relationships, and rules behind a graph. And this enables reasoning, the automatic inference of new facts from existing ones. So on the left here, you have a property graph where nodes carry buckets of properties, whereas on the right, you have the same data expressed as RDF triples. So this is just a fancy term for the subject predicate object model that we have represented there in the network itself. This structure is more rigorous, and that enables the reasoning I just mentioned. So in this case, this artist, we can reason that they signed to a label because there was an album released under that label. And that's something you can't necessarily do on the left-hand side due to the fact there's no formal scheme or ontology for the label property graph. Now, there are different tools for different problems. Property graphs are more common in the databases we'll be looking at today. I've done a whistle-stop tour of graph concepts, but the terminology doesn't stop here. Folks have come up with ways to apply graph thinking to basically any domain. Fraud detection, network topologies, supply chains, identity resolution, the list goes on and on. At G.V, we support customers doing all of these things, and regardless of the specific language or technique, it all comes down to the connected nature of the data. Now, AI, of course, has reignited interest in the use of graphs to help with things like context management and retrieval. Watch out for people saying things like hypergraphs, which again is another fancy term for just generalizing some of the concepts I've already described today. So you've seen the landscape of over 100 databases, various query languages, and different categories and trade-offs. At some point, someone always asks, can't we just use Postgres? The rest of this talk is about a particular extension that lets you do exactly that, and about what happens when you need to actually see the graph data that comes back. There have been several attempts to bring graph capabilities into Postgres. At the simplest level, on the far left there, you can bend Postgres to your will with stored procedures and recursive common table expressions. It works, but it's pretty painful and verbose, and I'll be showing you an example of that shortly. PG routing, or routing, depending on your pronunciation, is an extension feature focused on geospatial routing or routing. Shortest paths between road networks, that sort of thing. You can repurpose it for general graph queries, but it's not built for that, and the API reflects that. I've included gel at the bottom of the slide here, previously known as EdgeDB, which was confusing because people kept thinking it was a graph database in itself. This was acquired by Vercel last year, and it's kind of more of an ORM alternative to people who are familiar with that. And it's got graph concepts baked in on top of Postgres, but it's not really a database in itself. Apache AGE on the right-hand side there is the real focus of today, so let's dive in on that. AGE stands for A Graph Extension. Great name. It was originally developed in 2019 by a company called Bit9 Global, inspired by a fork of Postgres at the time, Postgres 10. It entered the Apache Incubator in 2020, and it became a top-level project in 2022, which is cool because it's the first graph database to do that with the Apache Software Foundation. It supports and works against Postgres 11 through 18. It uses OpenCypher for graph queries, and it's actually available on Azure database for Postgres, Horizon DB, and a few other providers. And in the real world, it's used across government agencies, research institutions, and a range of commercial organizations. As for the technical side, the architectural pitch is pretty straightforward. Relational and graph querying in one box. AGE leverages Postgres' query optimizer, its B-tree indexing for graph traversals, and the existing table hierarchy. So you get ACID transactions, MVCC, and all the Postgres infrastructure you already know. And Cypher is nice. People like the ergonomics of writing Cypher queries. At gdotv, we made it so you don't even have to worry about the SQL wrapper there. You just write Cypher and you get results back. So it's fantastic if you're migrating from, say, Neo4j, which is mostly Cypher itself. So to make all this concrete, I put together a graph data model based on something developers know really well, a source code repository. I took a batch of recent commits to Postgres itself, the version control history, and I built this model of authors committing to files with a self-referential sort of relationship between files based on their includes and imports. So an author commits something against a file, and the file may import other files across the rest of the code base. And here's what a query against this structure looks like in that pure Postgres example, that pure SQL example that I mentioned earlier with the CTEs. This isn't the whole thing. I've cut it off on the slide. It's about 50 lines, and there's a fair amount of boilerplate and kind of brittle SQL to make Postgres do something it wasn't really designed for in a sense. You wouldn't want to maintain a function like this in practice. PG routing is similar, and it's simpler. You can see we're using the driving distance function, which tells you it's not really purpose-built for general graph queries. It kind of cares about things like cost of driving to a particular location, but it does work. And I say it's simpler. The lines of query language here are a lot shorter than before. So here I'm finding the collaborators for one individual within a certain number of hops. So if somebody's committed to Postgres, what files have they been collaborating on with the set of other individuals who are committing as well. And here's our final example of a bit of query here doing the same thing. So this is in Apache AGE. This is our familiar select syntax with a subquery containing embedded Cypher inside those double dollar signs. That section there is just OpenCypher, the graph pattern matching I showed you earlier, and it's wrapped inside the SQL that you already know. It's more expressive, it's more contained, and it directly reflects the structure of the question that you're asking. Now, one more thing before we move on. SQL PGQ is the standards-based approach that I mentioned earlier. It's actually just being committed to Postgres core, targeting version 19. It's not guaranteed to be in the next release, but it's definitely something to keep an eye on if you're interested in this space. In contrast, Apache AGE is available now. It's mature. It's on all these cloud providers, and it's shipping pretty much anywhere that you're set to use Postgres. So now we have our data in graph format inside Postgres via AGE. We can query it with Cypher embedded in SQL, and the responses come back as rows, node IDs, edge types, properties. So this view is just a simple table that I've taken out of gdotv. It's informative, but I would say it's pretty uninspiring. And there is a time and a place for using tables. That's not a problem. But what happened to all those nodes and relationships I was talking about? Let's talk about visualization. These are your sorts of de facto data visualizations. If I imagine like a cartoon character asleep dreaming of data viz, this is probably what they're thinking of, like bar charts, pie charts, maybe a scatter plot not shown here. And they're good at what they do, pointing out the frequency of events, the distribution of those events, categorical breakdowns like there on the pie chart on the right. But notice what they're doing. They're summarizing. They're deliberately throwing away the connections between data points because that's what makes the summary useful. If I show you a bar chart of how many files each author committed to in our Postgres example, you get a summary, but have to dig further to get the details. You can't trace that dependency chain from one file to another through shared contributors with a pie chart. Sankey diagrams like this one, like the one you saw right at the beginning of the presentation, they get closer to what we're looking to represent here in the visualization. There's a sense of flow, of proportion, of things being connected. On the far left there, you see a large proportion of those data points are flowing through to another large proportion, which then get distributed to an even larger portion on the right-hand side. At gdotv, we include Sankeys as part of dashboarding, which is a bit unusual for a graph tool because most people favor the graphs I'll be showing you shortly. But there are real cases where this is the right representation. Typically, anything where flow through a system matters. But it's still fundamentally a flow view. It doesn't handle arbitrary connections, cycles, or the kind of tangle structure that a real graph has. And so here's where most people start. They get their graph data into a tool, they hit visualize, and everything lands on the screen. And this is the moment of awe. Look at all those connections. Look at how complex it is. If you look closely in the middle of the screen there, you can see there's a central node and there's lots of individual little nodes there around the edge, sort of like a swarm of bees around that node. Um, in the visualization here, that actually represents the fact that those aren't connected anywhere else. They're just sort of child nodes off that middle node there, which is something that's interesting when you look at this visualization, and not something that you get from a table. It is complex. This view is extremely complex. Complexity on screen isn't insight. Instead of answering questions, we're drawing pretty pictures. And yeah, I get it. It is pretty, and it is enticing to do this sort of visualization. But what typically happens in production or when people are prototyping is they go, okay, that's interesting. And then they move on because staring at this, sometimes they're affectionately known as hairballs. It doesn't tell you anything that you didn't already suspect, which is your data is complicated. And what's worse for me is that folks don't realize that these force directed views can and should be tuned for maximum impact. To my eye, this global view of the dataset isn't actually the best representation of these dense connections. It's overlapping, and you literally, or figuratively, sorry, you can't see the wood for the trees. So folks get distracted with looking at the wrong big picture instead of thinking of ways to subset and zoom into parts that warrant further inspection. So the idea behind these force-directed graphs, which I'll just dig into a little bit further, so you have a knowledge of the theory behind them, is it's based in physics. It's kind of grounded in physics. So nodes themselves repel from each other, and you can see that's happening. So this earlier example here on the left-hand side show that there are nodes closer together by the end of the layout run. They're further apart. And the edges, this is critical, the edges act as springs. So they don't get too far apart from each other before springing back. And there's lots of parameters you can use to affect how these layer engines work. But there's lots of great heuristics online for how exactly they should be working to get nice looking networks. So what happens is clusters of highly connected nodes pull together, whereas loosely connected regions drift apart. So you remember all those little example nodes, the child nodes in this view here. They're not going anywhere because they're actually only attached to that node right there in the middle of the screen. There's a lot of really rich research in this area. For large networks, Force Atlas 2 is the sort of state of the art algorithm that's out there right now. It works with very large volumes of data, and I've seen it do great results on quite complex networks. But one takeaway for you today is that no single configuration of these uh, will 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 work for all different types of data. This is something that you have to tune. You have to understand a little bit about what it's doing in order to influence how it should represent the data for you. But going back to what's attractive about these is that people intuitively get what they're looking at. The spatial arrangement reflects the connectivity and role in the network. With our Postgres commits data, you can see 6 authors here from those queries I was running earlier, the files they're committing to, and the clustering around their shared contributions. This was invisible in that tabular output I showed you before. But a node's position only represents the connectivity. That's all the algorithm has to work with. It doesn't know about the direction, the hierarchy, the categories, the timestamps, any of those semantics in your data. It's surfacing a single dimension, who is connected to whom, and just how densely. Structured layouts are different. Instead of letting physics dictate where the nodes are going, you use attributes from the data to inform the arrangement. The file dependencies in our commits example have a direction, includes point somewhere. This isn't a case of a bidirectional link where two files are referring to each other. There is a direction there between the imports between those files. If you lay that out hierarchically, the parent-child relationships become legible in a way that the force-directed layout flattens or reorientates. And this matters most when flow through a system is important. Attack paths, dependency trees, any use cases where direction and sequence are part of the meaning. A force-directed layout highlights how things are connected, whereas a structured layout like this emphasizes dependencies of those connections, direction, layers, hierarchy. The most powerful use I see for these is when teams pick a specific attribute from their data, category, severities, timestamps, and they use that to dictate the spatial arrangement on the screen. There's a useful distinction in the data visualization world, and this is the wider world, not just graph visualization, and that's between exploratory and explanatory work. Exploration is the analyst's job, querying, poking, forming hypotheses. Explanation is audience facing, communicating what you found to someone else. Most visualization falls cleanly into one camp or the other. Graph visualization is interesting because it sits right at the intersection of the two. When you're querying against your age data and looking for the result in a force-directed layout, that's exploration. You're trying to understand the structure. And most graph views, including gdotv, allow you to double-click and expand and explore networks in a way that you can't really do with a pie chart or even a dashboard like the one I'm showing here. The moment you share that same view, the same expansion with a colleague and say, look at this cluster, it becomes explanation. And the teams I see getting real value from this, some of them have GW open all day. They're moving between those two modes constantly. Explore, find something, share it, discuss it, go back and refine. And in this sense, the visualization, the graph visualization, isn't the end goal. Instead, it allows you to understand the data thoroughly and guides how you can communicate it to others. There's no right way to do graph visualization, but there are sorts of like infinite ways to do it wrong. And most of them involve treating the picture as the destination, as if rendering the data is the same as understanding it. The best graph visualizations I've seen, anything that takes a complex topic and makes it legible for a general audience, they share one trait. The visualization itself is in service of a question. It's clarifying something. It's not depicting complexity for the sake of it. What I care about at G.V is the moment when someone sees their data in this interactive format after running a query, typically maybe against something like Apache AGE, and it relies on their expertise, but it shows it in a way that they hadn't considered. The best reactions aren't, that's pretty. It's a pause and then, I didn't realize that connection was there. Or, wait, that data looks completely wrong. Or, did we really build the model like that? And that's where I see Apache AGE with Postgres really shining. The ergonomics of querying against the connected data and the traditional data visualizations in one database is pretty appealing. So, in summary, Apache AGE is open source. It's a top level Apache project, and it's available on all major cloud platforms, including Azure. It brings the popular Cypher graph query language to Postgres without adding yet another database to your stack. But those intuitive graph queries are only half the story. The traversals, patterns, and graph results need visualizations designed to emphasize connections. You've got force-directed layouts to surface structure you didn't know was there, and structured layouts to overlay meaning from your domain. Thanks so much.